Hello class, this is Ms. Riggins with today's video on sections 5.1 and 5.2, how do we measure distance traveled and the definite integral. As you're watching the video, I encourage you to take notes and write down important information, statements, equations, formulas, patterns, or graphs, and feel free to pause, rewind, or replay the video as often as you need to get a better understanding. After you have finished watching the video, please write down a brief summary of what occurred in the video and then submit that summary as well as a top question via the online WISC before class. All right, let's begin. So today we're going to revisit a previous type situation that we visited probably about a few months ago regarding how do you measure speed. And instead of measuring speed today, we're going to be measuring distance. So let's say I have information about how a car traveled in 10 seconds. And the information I have is the velocity of the car every 2 seconds. And the question is, well, I have the velocity and I have the time, but I don't know how far the car actually traveled. Well, there is a way to compute that because, as you know, velocity is distance divided by time. And since I have the velocity and I have the time, I can determine the distance they traveled. So for example, over here, at time 0, it says the velocity was 20 seconds. And then I can assume that for the first 2 seconds, the car traveled 20 feet per second, which meant you get a total distance in the first 2 seconds of 40 feet. And then I can say, well, the next 2 seconds, the car traveled 30 feet per second, which is a total of 60 feet. Vice versa, next 4 seconds, it traveled 38 feet per second, which is a total of 76 feet. And the next, I'm running out of things. Next 2 seconds, it traveled 44 feet per second for a total of 88 feet. And then let me go back over here and start the last 2 seconds, it traveled at 48 feet per second for a total of 96 feet. And then, so that means that I have a total distance traveled of 360 feet. But then some of you may be saying, how can you assume that you traveled 20 feet per second for the first 2 seconds? Why not you traveled 20 feet at the very 0 second, but then traveled 30 feet per second for the first 2 seconds? And if we do that, then instead of starting off with 20 feet per second for 2 seconds, we start off with 30 feet per second for 2 seconds, and then we do 38 feet per second for the next 2 seconds, and then we do 44 feet for the next 2 seconds, and then we do 48 feet for the next 2 seconds, 48 feet per second, sorry, for the next 2 seconds. And we end up with, for the last 2 seconds, 50 feet per second. And if we do it that way, then that means that now we have an estimate of the distance traveled being 420 feet. So which is better? Doesn't matter because we don't know for sure which is the correct answer yet. So both of them are estimates in this sense. And so I can say regardless of which one is better, I know that the actual total distance traveled will have to be somewhere in between 360 feet and 420 feet. And so in order to get a better estimate, which is not 60 feet apart from 360 to 420, then we can take a look by doing more in-time data collection. So instead of just looking at how the car traveled every 2 seconds, let's collect data at the velocity at every 1 second. And so that gives us more information about what was going on between seconds 0 and 2 and 2 and 4 and vice versa. And using the same strategies, the first strategy of starting off with the first second, they went 20 feet per second and vice versa, and getting all the way up to the first 10 seconds, but only using these values to compute that, we end up with a distance traveled of 376 feet. Whereas the other end, if we start with the first 0 seconds to 10 seconds and assume they went 26 feet per second, we end up using all those values from then on, which ends up with a total of 406 feet. So this is a little bit better estimate because instead of being 60 feet apart, from lower to upper as the previous one is, now we're only 30 feet apart in our estimate. So that's getting us closer and closer. And to get a better estimate, we would need to take, again, collect more data at more smaller time intervals than before. Graphically, let's take a look and see what's going on right here. And as we can see graphically, this being the velocity function, that these rectangles, the light blue one and the taller blue one, represent the area of the rectangles, and we're approximating the area underneath this curve to end up with the distance traveled. And as you can see here, the intervals are 2 feet, the intervals here are 1 feet. And you would say, well, this is a better estimate because you have smaller intervals, and that's actually correct. But the difference between the two can be calculated the same, which is, and this is something interesting to note, the distance between these two rectangles is the difference between the previous function values. Same here. Okay, we stop. So I can calculate that by finding the area of those rectangles with those height, and we all know that the width of each of the rectangles is going to be consistent for each strategy. So this width is going to be 2 feet per this rectangle, per the height of this rectangle, vice versa, and this is 1 feet per rectangle. So we have a way of approximating that error bound for each of the intervals that we chose, and that's by taking the difference between the highest value and the lowest value, which for each set is still 30, and then multiplying it by the width, which ends up being the length of the time interval, which is 2 and 1 feet. Okay. So again, if I want to get a better estimate, I take more data points, more closer time intervals, and instead of 1 second, make it a half a second, make it a fourth a second, whatever. But eventually, if I take enough interval data measurements and add them up, I will eventually get exactly the area under the curve. And that is what we want to talk about. The area under the curve is the same exact value as the distance traveled. If the velocity is positive, we have a way of determining the distance traveled by basically calculating the area under the curve, either using an approximation method with the rectangles, either the lower limits or the upper limits, or vice versa. So today we're going to talk about how do we do that. Now I know some of you may be saying, well, this is if the velocity is positive. What if the velocity is not positive? Well, then we will still use the same strategy, but we can't add negative velocity areas because that will take away from our total area. So we have to look at the positive value of the area between the curve and the x-axis. Okay? So let's move on to the very last one. Section 5.2, the definite integral. Before we start the definite integral, I want to just use some very general terminology. In our previous problem, our time interval was between 0 and 10 seconds. So let's just let A and B be any time interval on the domain. And let's reference A being the first value, left endpoint, as T naught, and B being T sub n, where we now have n+1 time intervals that are evenly spaced apart. And you can calculate what delta t, which is the distance between each time interval, is by basically breaking up the length of the interval into n different rectangles. And there you'll get the width of each rectangle. And so in order to determine what we call the left-hand sum, where we start with evaluating the function at the a value, as we see right here, remember a is the same thing as t naught, then we end up with something that looks like this. And then if we do what's called the right-hand sum, by starting off the evaluation not at f at a or t naught, but f at t1, we're going to end here with f of b, which is t sub n, as we saw in the previous one. So this is just a generalization of problems like the previous one. To determine the difference between the upper and lower estimates, as we saw, remember we subtracted 20 from 50. Well, 50 was f of b and 20 was f of a. So and then we multiply that difference by the delta t, how far apart each time interval was. So to find the difference between the upper and lower estimates, we do the exact same. We just use absolute value in case the values are negative, but we still want to be able to take their difference and then multiply them times the delta t, and we'll get our actual error estimate. So I want to give you some notation that's very helpful. Some of you may remember this from pre-calculus. This is called sigma notation, where sigma is this Greek, the capital E in the Greek alphabet. And at the bottom we have, in the top we have two values. The starting value with the index that we're using, in this case I, and the ending value with the ending value. So as we see here, we start off with t naught. So we're going to evaluate at each step the function at ti. In this case, we start off at t naught, and then we increase the index by 1 and do it to f of t1, and we end all the way up with f of t sub n minus 1. So this is the left-hand sum notation. We do the exact same thing with the right-hand sum, notation. But instead of starting with I equals 0, we start with I equals 1. And instead of starting with ending with I equals n minus 1, we end with I equals n. And so therefore we get the exact same expression if we were to add all these. And sigma means to add each of these different steps. So it's the same thing we did before. It's just a different notation where we don't have to write as much. But you are responsible for knowing that. So what would happen, as you saw before, that if we increase the, we decrease the time intervals, we get a better approximation from 2 to 1 to half a second to a fourth a second. We get a better approximation. Well, what happens if we let the number of time intervals go to infinity? Then our answer will end up being something called the definite integral. And this basically means from A to B, the area between the function and the x-axis, in this case the t-axis. And we can determine that by basically letting n go to infinity and calculating or determining the left and right hand limits with n subdivisions as n goes to infinity, as we can see here. So both of these, the limit of the left-hand sum and the limit of the right-hand sum as n goes to infinity, equals what's called the definite integral. And the definite integral is this. We call these sums the Riemann sum because we're finding rectangles. He came up with this strategy, I guess. And then we call the function f the integrand. And a and b are called the limits of integration. I know that may sound weird, but they're the limits of integration. And you can calculate this using the Riemann sums or even your calculator. And a little bit later, we're going to show you another strategy to collect them. So in closing, just want you to know that the area under the graph of f and above the axis between a and b can be computed by something which is called the definite integral. Okay, and we can approximate that by either using rectangles, computationally, a bunch of different rectangles, or we can evaluate this later by using the definite integral, which we will learn more about later times. And I know we took the condition that f has to be positive, but if f isn't positive over the entire interval, but is negative for other integrals, then the definite integral is still the sum of the areas above the x-axis, but we count that some positive, and then we take the areas below the x-axis, which would end up with a negative area. We count those negative areas negatively, so now it becomes positive. So we're basically still adding up only positive numbers. Now the Riemann sums don't have to be the same interval apart. the same unit apart, it will work forever, but the approximation might not be as accurate in general, but we can use this sigma notation to represent that, where we still have the function value, but instead of delta t being one value, delta t is changing in value. So you have another set of data. And that's it. Sorry the video was too long, but we had 2 sections and you have a long, so hope it went well. Bye-bye.